10.7 Power Series. The outline of this video is as follows. We will begin by formally defining what a power series is, showing how it resembles an infinite polynomial centered around a particular point. After establishing the definition, we will investigate the crucial concept of convergence. Since a power series contains a variable, its convergence is not a simple yes or no. Instead, it depends on the specific value of that variable. This dependence leads us directly to our third topic, the radius and interval of convergence. These terms describe the precise range of values for which the series converges to a finite number. Finally, we will synthesize these concepts into a practical, step-by-step method that you can use to test any power series and determine its exact interval of convergence, including how to handle the endpoints of the interval. Let us begin by defining a power series, which you can think of as a polynomial of infinite degree. This structure is incredibly useful for representing more complicated functions. The first form shown here is a power series centered at x equals 0. It is the sum from n equals 0 to infinity of a coefficient c sub n times x to the power of n. When we write out the terms, we get c naught plus c1 times x plus c2 times x squared, and so on. The values c sub n are constant coefficients. The second form is the general case, a power series centered at an arbitrary point x equals a. Here, each term is a coefficient c sub n multiplied by the quantity x minus a raised to the power of n. The constant a is called the center of the series. You can see the first form is just a special case, where the center a is 0. The most important idea here is that for the values of x, where this infinite sum converges, the power series defines a function of x. Let us explore our first and most important example, the geometric power series, which shows how a simple function can be represented by an infinite polynomial. If we take a power series centered at 0 and set all the coefficients, c sub n, equal to 1, we get the series 1 plus x squared, and so on. This is a classic geometric series with a first term of 1 and a common ratio of x. We already know that this series converges when the absolute value of x is less than 1. Within this interval, its sum is equal to 1 over the quantity 1 minus x. This gives us a powerful new perspective. We can think of the function f of x equals 1 over 1 minus x as being represented by this infinite polynomial, but only for x between -1 and 1. The partial sums of the series, which we can call p sub n of x, are finite polynomials that act as approximations to the functions. The key takeaway is that we can use these simpler polynomial functions to approximate the original function within its interval of convergence. This slide presents figure 10.14, which gives us a visual understanding of how partial sums of a power series can approximate a function. We are looking at the function f of x equals the fraction 1 over the quantity 1 minus x, which is shown as the red curve. The other curves are the polynomial approximations we get by taking a certain number of terms from the corresponding geometric series. For example, the approximation y sub 0 is just the constant one, a flat line. The approximation y sub 2 is the parabola 1 plus x squared. Notice that as we increase n, going from the straight line for n equals 1 up to the polynomial for n equals 8, the approximation gets significantly better. The polynomial graph hugs the function's graph more closely, especially for values of x near 0. However, this also illustrates a crucial point. The approximation is only good within the interval of convergence. As x approaches 1, where the original function has an asymptote, the polynomials diverge from the function's true value. The key takeaway is that more terms give a better approximation, but only within a specific range of x values. Let us analyze a power series that is not centered at 0 to see how the principles remain the same. This example shows a series centered at a equals 2. We can recognize this as a geometric series where the first term is 1 and the common ratio, r, is -1/2 times the quantity x minus 2. For any geometric series, convergence requires the absolute value of the ratio r to be less than 1. Applying this condition, we set the absolute value of -1/2 times the quantity x minus 2 to be less than 1. Solving this inequality reveals that the series converges when x is on the open interval from 0 to 4. Within this interval of convergence, the sum of the series is given by the formula 1 divided by the quantity 1 minus r. Substituting our expression for r and simplifying the algebra, we find that the sum is exactly 2 over x. Thus, we have found a power series representation for the function 2 over x that is centered at x equals 2. The convergence of a power series is not random, it always occurs over a well-defined interval. This slide presents the key theorem that establishes this predictable behavior. The theorem has two parts. First, if a series converges at some point c, it is guaranteed to converge absolutely for all x closer to the center than c is. Second, if the series diverges at a point d, it must also diverge for all x that are further from the center. These rules together imply that every power series must fall into one of three categories. The most common case is that there is a positive number, which we call the radius of convergence r, that defines an interval. The series converges absolutely when the absolute value of the quantity x minus a is less than r, and it diverges when this absolute value is greater than r. The second case is that the series converges for all x, which means r is infinite. The third case is that the series converges only at its center, x equals a, so r is 0. The essential result is that every power series has a radius of convergence r that determines its interval of convergence. Theorem 18 guarantees that the points where a power series converges form a continuous interval around its center. This let us define two fundamental concepts for any power series: its radius of convergence and its interval of convergence. The radius of convergence, denoted by a capital R, is a non-negative number that describes the size of this region. Within a distance r from the center, a, the series converges absolutely. Outside this distance, the series diverges. This radius defines an open interval from a minus r to a plus r. The full interval of convergence consists of this open interval plus any of the two endpoints where the series might also happen to converge. The behavior at these endpoints, x equals a minus r and x equals a plus r, must be checked separately, as the radius of convergence itself does not determine it. Therefore, the radius of convergence gives the size of the convergence region, while the interval of convergence is the complete set of x values for which the series converges. This slide outlines a reliable three-step procedure for finding the interval of convergence for any given power series. First, we find the radius of convergence, r. To do this, we apply the ratio test, or the root test, to the absolute value of the series terms. This process will typically give us a limit, L, that is proportional to the distance from the center of the series, a. For instance, L might equal a constant, k, times the absolute value of x minus a. We know the series converges absolutely when this limit L is less than 1. Solving this inequality shows that the radius of convergence, r, is simply the value 1 over k. Second, we must test the endpoints of this interval. The ratio test is inconclusive when the limit is exactly 1, which occurs at the points x equals a minus r and x equals a plus r. So for these two specific values of x, we must use a different tool, such as the alternating series test or a comparison test, to determine if the series converges or diverges. Finally, we state our conclusion. We know the series converges absolutely inside the open interval defined by R and diverges for all x outside of it. Combining these results with our findings from the endpoint tests gives us the complete interval of convergence. Let us work through an example to find the complete interval of convergence for a power series. This process combines the ratio test for the open interval with a separate check of the endpoints, which is a crucial step. First, we apply the ratio test to our series. The absolute value of the ratio of consecutive terms simplifies to the fraction n over the quantity n plus 1, all times the absolute value of x. As n approaches infinity, this limit becomes simply the absolute value of x. For convergence, this limit must be less than 1. This tells us the series converges absolutely for x, between -1 and 1, and the radius of convergence is 1. Now we must test the endpoints. At x equals 1, the series becomes 1 minus 1/2 plus 1/3, and so on. This is the alternating harmonic series, which is known to converge. At x equals -1, the series becomes -1 minus 1/2 minus 1/3, and so on. This is the negative of the harmonic series, which diverges. Therefore, the power series converges on the interval from -1 to 1, including the endpoint at 1. Power series are incredibly flexible because we can perform many standard mathematical operations on them, much like we do with polynomials. This slide provides an overview of the key operations that make power series such a powerful tool in analysis. First, within their common interval of convergence, you can add and subtract two power series term by term. You can also multiply them together, following a procedure very similar to multiplying two polynomials. Furthermore, we can create new series through substitutions. If you have a known series for a variable x, you can substitute a function of x, let us call it f of x, as long as the absolute value of that function remains within the original radius of convergence. Perhaps most importantly, we can apply calculus. A power series can be differentiated or integrated one term at a time within its interval of convergence. A remarkable and convenient fact is that performing term-by-term differentiation or integration does not change the radius of convergence of the series. The key takeaway is that power series can be manipulated algebraically and with calculus, allowing us to build new series from ones we already know. One of the most useful properties of power series is that we can differentiate them just as we would a simple polynomial. This powerful idea is formalized in the term-by-term differentiation theorem. It tells us that a function defined by a power series is differentiable inside its interval of convergence. To find the derivative f prime of x, you simply differentiate each term of the original series one by one. Let us look at the example of the geometric series. We know that the function 1 over the quantity 1 minus x is equal to the series 1 plus x squared, and so on. Applying term-by-term differentiation, the derivative of the constant 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, and the derivative of x cubed is 3x squared. This process gives us a new power series, which represents the derivative f prime of x. Crucially, this new series for the derivative has the same radius of convergence as the original series. Just as we can differentiate power series, we can also integrate them term by term, which is another powerful way to generate new series representations from ones we already know. Theorem 22 formalizes this idea. It states that if a power series converges on an open interval, we can find a series for its integral by simply integrating every single term of the original series. the resulting integrated series is guaranteed to converge on that same open interval. Let us use this to find a series for the natural log of the quantity 1 plus x. We can get to this function by integrating 1 over the quantity 1 plus t. So, we start with the familiar geometric series for 1 over 1 plus t. Then, we integrate this entire series from 0 to x. The integral of the first term, 1, is t. The integral of the second term, negative t, is negative t squared over 2, and so on. Evaluating this result at x gives the final power series shown here for the natural log of 1 plus x. The key takeaway is that term-by-term integration is a valid method for creating new series from old ones. We can often identify a function from its power series representation by differentiating or integrating it to find a more familiar form. This example demonstrates that powerful technique. We start with the given series for a function f of x. If we differentiate this series term by term, we get a new series for its derivative, f prime of x. This resulting series is 1 minus x squared plus x to the fourth, and so on. We can recognize this as a geometric series with a first term of 1 and a common ratio of negative x squared. The sum of this series is 1 over the quantity 1 plus x squared. Now that we have a simple expression for the derivative, we can integrate it to find the original function f of x. The integral of 1 over the quantity 1 plus x squared is the inverse tangent of x, plus a constant of integration, c. To find this constant, we look at the original series. When x equals 0, every term is 0, so f of 0 equals 0. This requires the constant c to be 0. Therefore, the original power series is the Maclaurin series for the inverse tangent of x. Let us bring together the key ideas we have discussed about power series. The central concept is that a power series, which is a summation of terms involving powers of the quantity x minus a, defines a function on the specific interval where it converges. To find this interval of convergence, we have a two-step process. First, we use the ratio test or the root test to determine the radius of convergence, which we call r. This gives us an open interval from a minus r to a plus r, where the series is guaranteed to converge. The second, and very important step, is to test the endpoints of this interval separately. This series may or may not converge at the points x equals a minus r and x equals a plus r, and we must use other tests to find out. Finally, the most powerful property of these series is that, within their open interval of convergence, we can perform calculus operations like differentiation and integration on a term-by-term basis. This gives us a new power series that represents the derivative or integral of the original function. Remarkably, these operations do not change the radius of convergence, providing a powerful method for generating new series from ones we already know. To wrap up, here are 2 review questions that test the key techniques from this section. For the first question, your first step is to recognize that the expression is a geometric series. Identify the common ratio, which will be a function of x. Then, apply the convergence condition for a geometric series, which states that the absolute value of the ratio must be less than 1. This will give you the interval of convergence. To find what function the series represents, simply use the formula for the sum of a convergent geometric series. For the second question, start with the basic power series for 1 over the quantity 1 minus x. Think about what substitution you can make to get a series for 1 over 1 plus x squared. From there, consider how you can use term-by-term differentiation to arrive at the final target function. Pause here to work through these problems.